Okay, let's see if we can consider now the development really of an AC model for the transistor. All right. Now, what I want to try to do here is really sort of make this as simple as possible. And I'm really sort of starting off here from, as it were, a common emitter viewpoint. All right. Now, what I'll do a little bit later is also try to link this to really the way the textbook is doing this. Okay. All right, so the first question I'm going to ask is, you might ask, is what basically is the signal actually doing? All right, and so I want to relate this really to our characteristics. So, all right, if we've got a characteristic curve that looks like this is really a plot of what? IB versus VBE, all right? Now, for our work, we've assumed really that diode type second approximation. All right, now I just want to kind of back off from that just for a second so that we can sort of visualize what's going on from perhaps an AC point of view. Reality is that that is an exponential curve. Now look, sure, I'm going to exaggerate that picture somewhat. Okay, so I've got this exponential relationship for really the input characteristic. Now what I'm going to really try to do is I'm going to say if I've got my transistor sitting over here like this, all right, where this is the collector, this is the emitter, and this is the base over here, all right, really what I'm having a look at now is could I model, okay, for the transistor, perhaps the condition between the base and the emitter. What does it look like between the base and the emitter as far as the AC signal is concerned? Now, we'll get to that in just a second, all right? So look, let's look at our characteristic and let's say this, that we've biased our circuit such that basically this would be our base current, if you like, our DC base current, and this, of course, is resulting in really a VBE, a DC value of VBE. Now, admittedly, we've assumed that that VBE, right, is 0.7, and for the DC work, that's good. That's a fine approximation. All right, now let's consider, though, we've applied a signal to this circuit. What's it doing? Okay, well, it's causing a variation, is it not, in base current around that DC value. So we might see, for example, the base current going up to this value. We might see it dropping down to this value, once again, centered around that DC value. Well, that variation in base current here, which we could call, for example, delta IB, so that variation there in base current is actually producing a small variation really in base emitter voltage over here. And so really what we have sitting over here is a small variation, we'll call it delta VBE, all right? So the variation in base current producing a variation in base emitter voltage, okay? Now look, if basically we're operating on a straight line section of the curve here, and this variation in base current is not too big, then you might argue that really this looks pretty straight line. It looks as though this variation in base current is linearly related to this variation in base voltage. And that's interesting. A linear relationship between base current and base voltage. How would we model that? How could you model that effect? Well, look, this is very clumsy to write delta IB for the AC variation and delta VBE. Why don't we just write it this way, which is consistent with the way your textbook is talking about the AC currents and voltages. We'll just use lowercase IB, and here, over here, we will just use lowercase VBE, all right? So the text is using these lower cases to imply we're talking about AC voltages and currents, all right? Now look, the interesting thing is this, that really the slope, is it not, relates the variation in IB, that's little IB, to the variation in VBE, that's little VBE, okay? And so we could say that VBE is really equal to 1 over the slope, is it not, times IB. Now, if we're operating on a linear section of the curve, we've got voltage related to current, okay, linear relationship. Could we not say that this is looking like this? VBE is really looking like some resistance, RB we'll call it, times the current IB. And so really what we're saying then is between the base and the emitter of this transistor, so here is the emitter, between the base and the emitter, for the AC components now, it looks much like a resistor which we will call RB. Here is our base current, IB. Okay, now you've got to remember, we're now talking about the AC component of current and how it's related to the AC component of VBE, the voltage. Okay, and I'm saying that they're linearly related, okay, providing the variation in IB is not too large. And therefore, how could we model that from an AC point of view? We could say that between base and emitter, it looks like a resistor. We're going to call that resistor RB. Now remember, we are trying to develop an AC model for that transistor. So therefore, for our analysis, if we apply a signal, we should be able to use that AC model to come up with an AC equivalent circuit so that we can analyze for voltage gain and current gain and such like things. Now, going a little bit further, if we now look basically at the collector current, and we look at the collector current, let us say, versus the base current IB. Now, for our purposes, we've pretty much said that that's more or less a straight line. And when you've been in the lab, you've seen that it really is pretty straight. Okay, down here at low currents, it's not. At high currents, it's not either. Okay. Now, we've established by way of our DC voltage and resistors, we established, if you like, the quiescent base current. That's it there. Which in turn has established the quiescent or DC collector current. Now remember, what's going on? Well, the application of the signal has caused a variation, has it not, in current, IB, around the quiescent value, which in turn is producing really a variation in collector current, centered, if you like, around that DC or quiescent value. All right? So how are these related? How is this little IB, which is the AC current, related to this little IC, which is the AC collector current? Remember, the AC current centered around the DC values. How are these guys related? Okay, they're related by really the slope. Okay? And what's the relationship between IC and IB? What is that slope? Well, from our previous work, we know that basically the slope is beta. And so we can say little IC is really beta times little IB. Okay, and that's the same sort of relationship that we had for our DC work. Now, your textbook might talk about, for example, the DC beta and the AC beta. Okay? Now, for our purposes, we're going to assume those guys are the same. They will be the same if that is a straight line going through the origin. They will be the same, okay? And to all intents and purposes, they are very close. All right, so now we have an AC relationship between collector current and base current. So if we develop our model just a little bit further here, what do we have? Well, here is our base, and remember, between the base and the emitter, here is the emitter sitting over here. We said, I could model that for the AC effects by a resistor RB. Here is my defined base current, little IB coming in. Now, what about the collector over here? Well, the collector current, we said, is what? Beta times IB. Well, could I come up with some way to model that? Beta times IB. Well, maybe what I could do is I could take a current generator, okay? And I could say, well, this is really a dependent current generator, and its value is going to be beta times the base current IB. So this collector current, remember, there is your collector current IC. This collector current is simply this value of current generator, which is beta times IB. It's a dependent current generator. Its value is a function of the base current, as indicated really by that equation. So really all I'm doing is modeling that equation, and then I'll simply connect that to the emitter. And if we look at that circuit, what is the emitter current coming down here? Well, it's the base current plus the collector current. And so just as before, we've got IE is really equal to the base current plus the collector current. Same relationship that we had when we were looking at the DC analysis. Okay, key thing here is you've got to realize, okay, that these are AC currents and voltages centered around the DC values. And what we're trying to come up with is an AC model for the transistor. That's what we're really trying to produce here. Okay, we really should tie this in to the textbook. Now what I've tried to do here is develop this little AC model very simplistically, having an understanding of the input characteristics for our common emitter circuit, understanding the current, the collector current relationship to IB. I think you can very quickly and intuitively, as it were, reason this little model here. Okay? Now, just to take really this a little bit further, we need to talk about this RB. All right? So what is the value, or how do I evaluate, let's say, that little RB term? Now, in some problems, I'm just going to go ahead and give you that RB. RB, in fact, really has been, if you want to evaluate RB, sure, you can do it from the input characteristics. Remember, it is the slope at the operating point. And so if I kind of looked at those input characteristics again, there's IB, there's VBE. All right, we had this exponential characteristic. We have an operating point here. And remember, it's really that slope, isn't it, at the operating point. So there's the operating point. We're really having to find that slope. This is an exponential equation over here, which would basically require us to write down an exponential equation, differentiate that exponential equation, and determine its value at the slope. Okay, so its value should be determined at the slope. Now, the textbook really talks about another term called little re. Okay, it talks about little re, and I just want to relate my RB to the textbook little re. Okay, so that's where we're really heading with this. Now, VBE here, this is the AC VBE. VBE is really equal to little RB times IB. Okay, that's where we came up with this little model here. Now remember, this is the AC VBE. It is not 0.7. 0.7 was used for DC. Remember, we're talking about the AC component here. That's the value superimposed around the DC bit. Okay. Now look, we could rewrite this equation here in terms basically of what? Well, we could write it in terms of IE. So look, let's just take a moment here. Remember IE, we said IE was equal to what? 1 plus beta, as it were, times IB. Okay? And look, if the beta is large, we could say IE is what? It's really approximately equal to basically beta, I should say, times what? The IB value. Okay, and then just playing with this equation a little bit, we could simply say that what? IB is really equal to what? IE divided by beta. Now that relationship we looked at in the previous video, it's the same basic relationship there, except now we're talking about the AC components, and I've rewritten IB as IE over beta. Okay, I want you to certainly convince yourself that that is the case. All right, so what if I put this, as it were, this into here? What's going to happen? Well, I'll get VBE, okay, is equal to what? Well, putting in, I've got my RB sitting there, okay, so I put in this, I've got what, times IE, and that whole thing's divided by beta, isn't it? Okay. Now, in the text, your author talks about VBE in relation to IE, and your author is simply saying that, look, VBE is equal to RE times IE. Okay, so from the text point of view then, really the author's looking at this equation, VBE is really equal to RE times IE. So therefore, what's the relationship then between my RB and this guy here? Let's just very, very quickly look at that. Well, that must be the same as that, and so therefore I'll write down RB of a beta is really the same as the little re, and so therefore RB is really beta times little re. Okay, so I've now tied in my value of RB to the textbook little re. And the textbook will give you this. It's basically saying little re is 0.025 divided by I, this is capital IE Q. Now, this is a way to figure out that little re. All right? This number 0.025, okay, is basically, remember we spoke once before about the diode equation, and we had Boltzmann's constant, the electronic charge, etc., okay, and temperature in absolute or degrees Kelvin. Well, that's putting all that stuff in, and you come up with that 0.025, okay. The IEQ here, okay, is a DC current. It's the DC emitter current, the DC quiescent emitter current, and that's really used to evaluate this little re. Effectively what you're doing is you're evaluating little re really at, it's a slope, and you're evaluating, or 1 over the slope, and you're evaluating this at the operating point. Okay, so this is something that you might want to remember here. It's in the text, and if I look at the text, where is it in the text? You can see this really on page 295 and 296. That's really where you want to have a look at this. So what I'm doing here is I felt it was easier really to intuitively reason our model, basically from our input characteristic and our output and our current, collector current, base current relationship, and we could reasonably, intuitively get to that model. Okay, and then of course I think I need to just tie in my little RB basically into the textbook little re, but I do believe that is an easier way to go. But have a read of that, see what you think about that, and how I came from evaluating this RB to being beta times this little re. Okay? All right, let's take a break here. You have a think about that, and then we'll come back to this model and we'll try to use this model in some actual amplifier circuits.